Have you ever heard the thought, it's too dark in here, too loud, too quiet, whatever? Well, we may have a product for you. Our new project, the Sensotron, measures light and sound intensities throughout your house while at the same time providing a new robotics experience for young people. The Sensotron was initially built as a prototype using NXT motors and sensors through an NXT brick programmed through LabVIEW. Now, what we need you for? We need funding so that you don't have to go out and buy an NXT set. You don't have to program it. We want to be able to manufacture it on a large scale, break down the motors, break down the pieces, put it into a small convenient box or car that we can place in your house, in your garage, in your room, drive it around automatically, simple construction, while at the same time understanding the components and how they move, broken down into 3 parts. 1, the axle with the wheels. 2, the drive shaft. 3, the sensors. And 4, the main chassis of the car. Now, what the risks of this project would be is if you don't support us, we won't be able to make the project compact enough to be plausible for the everyday user to purchase, use in their house, and store. Storage is the main issue, transportation, it's large, it's bulky, and we need your funding to help perfect our project. So please support Sensotron.
So for our project, we wanted to make a self-driven robot that could run around in your house and detect light, sound, and temperature for different areas of the house. And the reason why we would want to do this is for improvements of house improvements for insulation or more lighting or barriers to stop sound going into another room or something like that.
So we began building this project with the thought of using either the Arduino or the NXT. So our first design was built strictly with Legos, no NXT brick, to try and make it so that you could arbitrarily put an Arduino or an NXT on there. When I built that, it was too bulky, did not balance, wasn't sturdy enough, and the final decision came when we found out the Arduino converter for the NXT only had 2 motor outputs, and as you can see we have 3, 2 for the front wheels and 1 for the axle. And so our final design was this. We have 1 wheel in the back which simply rotates with the car as to provide support for the rest of the vehicle. We have an ultrasound sensor which detects when a wall is or any object is in front of it, and it'll back up, turn, and then continue on its path. And then on top we have light, sound, and temperature to detect those intensities throughout a house or room or any area. For simplicity's sake, here's a diagram of how each sensor is hooked up to the Arduino. The 3 motors are hooked up to ports A, B, and C, and the sound, light, temperature, and ultrasonic sensor are hooked up to ports 1 through 4. These ports are used to import and output the data from the sensors and the motors using LabVIEW. So here we have the LabVIEW front panel. We have plot of the XY position on the left. We have light on the bottom and sound on the right, and temperature on the top. The 4 dialog boxes at the bottom are for actually saving the files. In the top left, you can see the slider bar. This is one of the inputs into the motors that allows the user to control the speed at which the NXT robot moves. That slide is also input into the XY position plot to account for the greater distance that it will travel. Here's the LabVIEW code. It has 5 arrays that initialize on the left. They go into shift registers. This is for the X and the Y positioning, as well as the temperature, sound, and light. This is very complicated LabVIEW. The case structure you see on the left is for the instance in which the robot encounters a wall or object. The first statement adds a specific number, which calls the second case, which then causes the robot to reverse, which then causes the robot to turn its axle, which then causes the robot to delay in order to back up and turn for a certain set period of time. And then the next two cases straighten the wheels out and have it continue forward again. The second case structure you see on the right is simply so that when you stop the file and begin to save the text files, which you can see on the very far right, it stops the wheels from turning, because prior to adding that case structure, which calls a break when the stop button for the program is pushed, the wheels would spin until all of the files were saved, and this was just simply inconvenient. I have a number of indicators for each of the plots to show that it is working and that there's no glitches in the program. So here's our calibration of light. It used various levels of light in comparison to the readings on a light meter from the optics laboratory, and we found an exponential trend. And here is our calibration for distance. Using a simple tape measure and running tests at different powers and over different distances, we were able to find a linear correlation between the counts from the sensor and the actual data.
So after the calibration, we put the robot down inside our house and we just let it run around for a little bit. And we put that data into MATLAB and we get what we see here. What we have here is XY plot of the robot's position, and each dot has a varying shade of gray to show the intensity of light at that position. We could, as you can see here, the top rectangle-looking thing is actually the hallway of the house, and as you can see, the dark dots are because the hallway is not very well lit. And the bottom and the middle triangle looking thing is the living room, is a little bit better lit, and at the very bottom right is the kitchen dining room area, which is extremely well lit. So here's a picture of the temperature versus position of the robot. This one didn't work out too well for us for two reasons. One was the varying temperatures in each room didn't vary as much as we hoped it would, and two was the resolution or the precision of the temperature probe was not big enough for us. I know it was too big for us, meaning that it didn't detect the small temperature changes varying in each room. So here we have the sound intensity versus the position of the robot. The sound intensity is measured in decibels, which is why most of it's in a very low range. You can see in the hallway that there's some instances of loud noises, which is when the robot went by some roommates' rooms. The biggest and most loudest place was in the bottom right, which is in the dining area, which is near the kitchen, and one of the roommates was cooking, and you could see that it picked up a lot of his activities in the kitchen. It's going.
Support us with $500 or more, and we'll provide you with an early release Sensotron. Think about it.